Good morning, students. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC702C. Topic: pulse cutoff conditions in magnetron. Eight cavity cylindrical magnetron. It consists of a thick cylindrical cathode at the center and a coaxial cylindrical block of copper as anode. The space between the anode and cathode is called interaction space. One of the cavities is connected to a coaxial loop to extract output. Basically, magnetrons are cross-field tubes, means the applied electric and magnetic fields are perpendicular to each other. Here, the magnetic field is supplied by a permanent magnet. Initially, we assume that some noisy voltage, RF noisy voltage, present in the interaction space. Based on the noisy RF voltage, the electrons generated by the cathode in between affected by the noisy RF field, they are velocity modulated, forms bunching by losing energy. The amount of energy lost in formation of bunching is transferred to the noisy RF field till the oscillations are sustained. The reason is energy cannot be destroyed, converted from one form to another form. Favored electrons transfer energy to the RF field. Unfavored electrons takes energy from the RF field. Constructional details in 3D. Pulse cutoff conditions. The magnetic field does not affect the velocity of electron beam. It simply bends the electron path. The velocity of the electron beam is given by V square is equal to VR square plus V pi square. VR is the radial component of electron velocity. V pi is the angular component of electron velocity. The relative phase change of AC electric field across adjacent cavities is given by pi V is equal to 2 pi small n by capital. Pi V equal to pi implies it is mode of resonance. Pi V equal to 0 means it is 0. Pulse cutoff condition. The equation for electron motion in a cylindrical magnet can be written as equation number 1, that is 1 by r d by dt r square d pi by dt is equal to E by m b naught dr by dt. Rearranging above equation, we get equation number 2, that is d by dt r square d pi by dt is equal to E by m b naught r dr by dt. Here omega naught is equal to E by m b naught. Omega naught is called cyclotron angular frequency. Integrating equation 2 with respect to t, we get equation number 3, that is r square d pi by dt is equal to half into omega naught r square plus constant. But we also know that v square is equal to vr square plus v pi square. Vr is a radial component, v pi is the angular component, and here the radial component vr is equal to dr by d pi. The angular component v pi is equal to r d pi by dt, and v square is equal to 2 ev naught by m. Let it be equation number 4. In case 1, at r equal to a means at the time of generation from the cathode, the electrons are having only a radial component of velocity. There is no angular component. So r d pi by dt at r equal to a equal to 0. Means at the time of generation from the cathode, the electrons are having only a radial component of velocity. Based on that, From equation number 3, we get the value of constant as minus half into omega naught r square is equal to minus half into omega naught a square. The reason is it is at the time of generation from the cathode at r equal to a. Substituting in equation number 3, we get equation number 5, that is d pi by dt is equal to half into omega naught 1 minus a square by r square. Once again, rewriting v square is equal to vr square plus a pi square, radial component of velocity and angular component of velocities. Case 2 at r equal to b means here the electron generated from the cathode just grazing the surface of the anode comes back towards the cathode, that is at the critical magnetic field. At critical magnetic field and at the position of anode cavity, the electron is having at this particular position, the electron is having only angular component of velocity. That is why the radial component of velocity is 0 at b naught is equal to POC. So the cyclotron angular frequency at critical magnetic field is equal to E by M BOC. Rewriting equation number 5 at R equal to B. We get equation number 6. From equation number 4, taking the radial component as 0, we get equation number 7. Substitute equation number 6 into 7, we get equation number 8, and by rearranging equation number 8 and substituting the value of cyclotron angular frequency at critical magnetic field, we get equation number 9, that is BOC, minimum magnetic field required by the electron to graze the surface of the anode comes back towards the cathode, that is BOC is equal to root of 8m V naught by E by B1 minus A square by B square. Now here this is the position of cathode and these are the position of anode cavities. Now here what it means is for a given V naught, if the applied magnetic field is equal to critical magnetic field, the electron generated from the cathode just touches the anode cavity and comes back towards the cathode. And here, if the applied magnetic field is greater than critical magnetic field, the electron immediately comes back towards the cathode. Means here, this means that for a given B naught, if B naught greater than BOC, the electrons will not reach the anode. And equation number 9 is called Hull's cutoff magnetic equation. Equation number 9 is called Hull's cutoff magnetic equation. Conversely, the cutoff voltage is given by VOC is equal to E by 8m B naught square small b square 1 minus A square by B square whole square. Equation number 10. What it means is for a given B naught, if V is equal to VOC for a given B naught, V is equal to VOC, the electron just grazes the surface of the anode and comes back towards the cathode. And here, if V less than VOC, the electron immediately comes back towards the cathode. Thank you. We will meet with the next lecture.